From Bloomberg News and iHeartRadio, it's The Big Take. I'm Wes Kosova. Today, to see the past, the present, and the future, just look up. Today, we're talking about two significant advances in science and technology that may not sound related, but they are. The first is probably familiar. It's the James Webb Space Telescope that's been beaming back these incredibly detailed images from galaxies far, far away. The other may be less familiar. It's NASA's SWOT mission. That's a satellite that uses something called remote sensing to take detailed measurements of the planet's surface water and ocean topography. So, SWOT. Together, these two things represent a leap in our ability to access space to gather vast amounts of data about the status of our planet right now and to look back in time and into the future. That's useful not just for pure science and discovery, but to make decisions about our everyday lives. Let's jump right in with the James Webb Space Telescope. And to do that, I have the help of my colleague, Lauren Grush, who's on the space beat for Bloomberg. Lauren, I want to start by asking you about the James Webb Space Telescope. I think we've all been looking at those amazing pictures coming back. It launched in December of 2021. Why is this thing such a big deal?
Well, you have to understand how astronomy works, right? We're essentially trying to map out our neighborhood without ever leaving our house. What a telescope like JWST does is it gives us an even bigger, magnifying glass, if you will, to look even deeper and farther into space than we can before. So it's not only is it located roughly 1 million miles from Earth. That's, extremely far, but also it has the biggest mirror that we've sent into space that can collect even more light than we've ever collected before. So that is our best tool for being able to see into the deepest recesses of the universe and learning more about, what the earliest galaxies looked like that formed right after the Big Bang.
I've heard it described as you're not really looking at distance, you're looking at time, because you're looking so far back in time. Anything you're seeing could be potentially billions of years old.
Right, because, light does take time to travel to our eyes. And so when you're gathering light from such deep distances, that light has spanned, billions of light years to reach JWST's mirrors. And so what you're really seeing when you look at those images is how those galaxies looked billions of years ago.
What was it like as someone who covers space to watch that thing launch? Was that like a big moment for just you?
Well, I like to say that the James Webb Space Telescope has kind of two chapters in my reporting history. People don't think about it now because it's in space and it's working as it's supposed to. But most of JWST's lifetime was marked by cost overruns and development delays. We had all these promises that it was going to launch, many years ago. And then, we would constantly get new updates. Oh, it's going to take more time. It's going to take more testing. And so, it was always kind of a long running joke. Was it ever actually going to launch? And would we actually be able to afford it before Congress pulled the plug? And then also there was just kind of a general terror, not just among reporters, but also among the astronomy community because of how JWST had to launch.
Producer Catherine Fink sat down with senior project scientist Dr. John Mather at his home in Maryland. Here's what he told her about developing the James Webb Space Telescope.
The biggest challenges were that it's huge. It's bigger than the rocket. And so it has to be folded up to fit inside the rocket. And it also has to be cold so that it doesn't emit its own infrared light. That means it's got to be protected by a gigantic umbrella, which we call a sunshade, that's as big as a tennis court. That also has to be unfolded in outer space. And because it's so far away from Earth, we can't go fix it if anything's wrong. So some major challenges here which require serious engineering. It was harder than we thought it would be. And we ran into budget trouble because, we just didn't know how hard it was going to be. So fortunately, our funding agencies, the Congress, the international partners, they all said, that's true, it's harder than we thought. But This is the only way to get this. So we better keep on going. And so we finally finished it and launched it on Christmas morning, 2021. And it was a perfect launch.
We were all kind of on pins and needles for a good solid month after it launched. But now we're in this new chapter, which is, the discovery phase. And I think most people don't even remember the first phase, the first chapter, because we're getting back such stunning imagery and amazing science from the telescope, which is what the astronomers and scientists and engineers worked so hard to achieve to begin with. So it's definitely all been worth it. And it has been nice to see the narrative change into discovery now.
And this was part of an international partnership. Who else is involved in the project?
Europe was also involved. They provided the launch vehicle for this, the Ariane 5, which launched JWST into space. And it actually did such a good job with its launch that it put it on a great trajectory so that JWST will actually last longer than they even anticipated. And so it really was a global project. I mean, scientists around the world are all vying for time on this telescope. So it wasn't just NASA. NASA was the one that, provided the bulk of the money. Northrop Grumman was the primary contractor, and then various scientists and astronomers from around the world are also involved.
Catherine asked Dr. Mather what questions he was most eager to answer about our galaxy.
The nature of the cosmic dark matter and the cosmic dark energy are very puzzling. Astronomers, physicists did not expect them. There was some evidence from a long time ago that they might be real, but we didn't expect them. We don't understand why they're there. And so we're all hunting for more evidence about that. Will we ever understand? Maybe not. What happened to grow the first galaxies? Every big galaxy has a black hole in the middle, a big one. They're called supermassive, so they're like 1 million or 1 billion times the mass of the sun. We don't know whether the galaxy made the black hole or the black hole made the galaxies. Which came first? We would certainly like to know, are there planets anything like Earth out there? So we know that there are planets of the right size and temperature to be like Earth. The next big step after the telescopes that we're already building is something called the Habitable Worlds Observatory. And it would be about the size of the Webb, only much more accurate and capable of making such a good image that you could see a little Earth next to the star that it orbits as a separate image. And then we could say, well, does it have water and oxygen and carbon dioxide and things like that? That would be a hint that it's alive. So here on Earth, of course, the oxygen comes from plants and algae. So if we find it out there, then we'll have a long discussion about what it means, but it's a hint that another little planet could be alive.
I think that's what's so exciting about JWST is that it really is designed to tell us things that we can't even give it prompts for, and to, look even deeper than we could even think possible. I mean, one of the most amazing parts of it was when it first launched, scientists were getting data back so quickly and analyzing it so fast that they were constantly breaking the record for finding, the most distant galaxy that's ever been found. And, they would find it one day and then like a week later, they would find another more distant one. So the rate at which we're learning new things from this telescope is so rapid and fast. And so I think it's only a matter of time before it's telling us something that we didn't even anticipate to look for.
When we come back, a scientist who will use the Webb telescope to peer into black holes. To hear more about the kind of data that's come in from the Webb telescope so far, Catherine checked in with Dr. Priyamvida Natarajan. She's an astrophysicist who studies black holes. Her team has been awarded time with the telescope later this year, and already all these new discoveries from other scientists using the instrument have kept her pretty busy.
You, of course, study black holes. Could you just give a brief description for those like myself who just have a hard time wrapping our heads around what a black hole is?
One way to think about a black hole is that it is a place where gravity is so intense that almost anything that comes close gets captured by the intense gravity. they are such strongly aggregated, dense clumps of matter. They're the end states of stars. So when stars burn out all their fuel, they explode and they can leave behind, if they started life as a pretty massive star, very compact objects. So for example, if the Earth were to behave like a black hole and have the intense gravity that a black hole has, we'd have to scrunch the entire Earth to the size of a penny. That's when that compact.
Wow.
And that's when its gravity would have the intensity of that of a black hole.
So what is a typical day like as someone who researches black holes? Is there a typical day?
There is no typical day. And in particular, with James Webb right now, I'm looking for any new findings about distant black holes. Where James Webb has imaged some fantastic nearby black holes. Two galaxies that harbor black holes in their inner regions are very, very dusty. So, James Webb has been able to cut through right into the heart of this galaxy, look at the dust, and given us a really clearer view than we've ever had before. And so we can actually see the impact of the black hole in the region around. So matter falls into the black hole, and some portion of the rest mass energy of the matter that is swirling in gets converted into radiation. So that heats up in the vicinity of the black hole. So these were all sort of, theoretically, we had worked this all out. And James Webb, JWST, is actually revealing all the sort of ionized hot gas that we expected. But now we're actually seeing it really up close. So it's pretty amazing.
Yeah, so you mentioned the distant black holes. What would those tell us if we're able to get data from the telescope versus the ones you just talked about?
Well, the distant black holes, obviously the question is of the origin, right? Where did the first black holes come from? James Webb has the capacity to look back into the infant universe and actually reveal the presence and catch the first black holes in action. So we don't quite know how the first black holes grow, whether, we think that the end states of stars could produce the first lot of black hole seeds. But there are also other physical mechanisms. So people like me and many other researchers have proposed like direct formation, bypassing the formation of a star and just forming a black hole just from the gas, in the early universe is so violent that you can actually condense a lot of gas very rapidly and make a seed black hole that is much more massive, much bigger than the ones you could get from the end states of stars. So I think what the first black holes really are, how they grow, because we believe that the black hole at the center of our own galaxy, right? The Milky Way has a black hole at its center that is 4 million times the mass of the sun. It's like wanting to see the picture of an infant when we see the picture of the fully grown adult or the aging person, right? So we want all the intermediate snapshots to build the sort of life history of how a black hole would form and grow. But meanwhile, what is super exciting is that James Webb has revealed the presence of early galaxies, many more galaxies in the early universe than we expected, and out much earlier in the universe. So it's like the clock of when things start, all the action starts in the universe, as it were, with stars forming. And seems like suggestions are that probably the clock is starting a lot earlier than our current theories led us to believe. So that would be super exciting. That would be radical. James Webb is also transforming our view of the nearby universe. So, for example, there's a first observation of a Earth-sized exoplanet system and its atmosphere. And that is just like awesome. We've never been able to do that, right? So remember, this just opens the door for studies of the composition of these atmospheres. And, it leads us to ponder some of the really big questions, right? Are there any atmospheres that are similar enough to ours or have the kind of composition that could support some kind of life, et cetera, et cetera. So it's kind of opening the window even in the very nearby universe with sort of radical observations.
Lauren, coming back now from black holes in the depths of space to something a little closer to home, NASA is at work on any number of missions. What is NASA doing right now that excites you?
NASA is trying to go back to the moon after all of this time. And this time they're trying to do it a little differently. So a few years ago, they officially named their Artemis program for the effort. And Artemis is a great name for it because she's the twin goddess of Apollo in Greek mythology. And the purpose of Artemis is actually to send the first woman and the first person of color to the moon. So that will be great in terms of its own historical significance. But it also differs from Apollo in that NASA really is trying to go back to the moon this time to stay. So rather than just sending, a couple of astronauts to the moon at a time to collect samples and leave footprints, that's their motto. It's no longer flags and footprints. They're looking to go sustainably. So creating infrastructure in and around the moon that will allow humans to live and work there long term so that we have a sustainable presence up there. It's an extremely ambitious endeavor, but I think it's what we're ultimately working towards when it comes to our space exploration goals. It's how do we improve upon the major achievements that we've done in the past. And so that's what I'm really excited to see. And what I'm also excited about is this program seems to have some staying power, more so than other ambitious programs have had in the past. This isn't the first time that we've tried to go back to the moon again, or even go onto Mars. But when it comes to administration changes, things can get wiped away. But this one survived an administration change, so hopefully it will survive another. And it would be great because that's how we make impressive things in space happen. They take a while, longer than 4 years of presidency. So I'm very excited about that, and I'll be following it as long as I am reporting on space.
We'll return to Earth when we come back. Lauren, we've talked about the moon and deep space. Now let's come back home and talk about NASA's new project called SWOT, that stands for Surface Water and Ocean Topography. And it uses this thing called remote sensing to survey the Earth. Can you tell us what remote sensing is?
Sure. So remote sensing is the technology that we use from space to observe our Earth. So that can be in optical wavelengths, that can be with radar, that can be with an infrared. It's using satellites to collect data about our Earth. So looking back at us, the ultimate selfie, if you will.
Why is it important to do this from high above the Earth? What do we get looking down that we don't get from all the different ways we're able to measure stuff from Earth?
Well, it gives us a more complete picture of the overall globe. So, for instance, remote sensing has been great for collecting data about our climate and observing it over time. So if we want to focus on one patch of the Earth and see how the climate in that area is changing, that's a great use of remote sensing and space technology. Another obvious reason is, if we want to look over a distant part of the Earth that is not very accessible, we're getting much more fidelity with the data that we can collect. And also the commercial space industry has taken a big foothold in remote sensing. Normally, this was an area solely taken by the government and the public sector, but now private companies are actually building technologies thanks to the proliferation of satellite technology, the miniaturization of satellites, the commercialization of satellites. They are the ones that are actually taking the lead and the reins on remote sensing as we move forward.
Yeah, let's talk about that for just a second. Who's sending these satellites up there?
NASA has been sending remote sensing satellites into orbit for ages now, but we have commercial companies like Leo Labs, for instance, and Planet and Spire. They're all launching small satellites that can look back on the Earth and collect data about it as well. I think the government has understood the benefits of turning those satellites back on Earth and looking and being able to collect data about the world that we live in.
One of those satellites is called SWOT. NASA loves its acronyms. Producer Rebecca Chasson talked to a couple experts to learn a bit more about what sets this particular remote sensing satellite apart.
So my name's Tamlin Pavelski. I'm a professor at the University of North Carolina, and I'm also the hydrology science lead for the Surface Water and Ocean Topography mission.
My name is Parag Vaze. I am the SWOT project manager for NASA's Jet Propulsion Laboratory in Pasadena, California. SWOT stands for Surface Water and Ocean Topography. It's NASA's next generation satellite mission that is expected to look at all of the global surface waters. That means what we might say fresh water and also our salt water.
So let's divide Earth's surface water into kind of two chunks, right? First, we've got the ocean. It's easy to think about the ocean as a bathtub, right? Where there's like one sea level. But in fact, the ocean surface has topography. It has higher and lower places. We have a current suite of satellite altimeters. They're called profiling or nadir altimeters. That allows us to kind of see features in the ocean that are maybe a couple 100 kilometers in size. And it turns out that most of the ocean energy, like most of the circulation in the ocean and the action in the ocean, is actually smaller than that 200 kilometer size. And so SWOT is going to provide us that first picture of like an order of magnitude smaller, of features like eddies and whirls and things like that that are down to maybe more like 20 kilometers rather than 200. One of the things that we know is that sea level, it's rising everywhere, of course, or almost everywhere, but it's rising at different amounts in different places. But our current set of satellites don't give us very good data right near the coast. So what we're left with is we have to use tide gauges, and we have some of them, but they're not evenly spaced around the world's coasts, and there's big spaces, big gaps in between them. SWOT is actually going to be able to see pretty much right up to the coast, and so we're going to be able to use it to better understand sort of how sea level rise might affect coastal communities. If you are going to want to think about what matters to you, when you're trying to predict a flood, right? If you're a homeowner, you probably care, where is the floodwater going to be and how high is it going to get? And SWOT observes both of those things simultaneously.
So with the standard altimeters of the past, how close to the coast could you get with those measurements?
Yeah, so we could get to something like 70 kilometers.
And how close will SWOT be able to get into the coast?
So we think we're going to get to something like 10 to 15 kilometers.
Wow.
So still not right up to the coast, but pretty darn close. And at much higher resolution, as I said. So, it's like saying pixels. Everybody knows about pixels and their monitors, right? So it's like saying, okay, I saw a few pixels on my screen, but now all of a sudden I'm able to, multiply the number of pixels I have by 10-fold or 100-fold. Well, I'm going to see a much better picture, much more clearly than what I saw before. And so the goal is to not only measure the height of the water, but also because we're taking these repeating measurements, it gives us a measurement of how that is changing. That is certainly something we can do very precisely with the measurement that I've mentioned to you. And when I mean very, very precisely, I mean within a few centimeters. So sort of the distance, the size of a quarter.
Tell me about what kind of picture we have right now of Earth's surface water. How much do we know?
Right now, we kind of monitor a few lakes, like the really big ones mostly, and then a smattering of smaller ones, but maybe 10,000, 20,000, something like that around the world. There's something like 6 million lakes larger than 100 meters by 100 meters in the world. And most of those, we have no idea what's going on in terms of the amount of water that's being stored in them. And SWOT's really going to help us with that. Lakes are these sort of sentinels of the water cycle. If you want to understand what's going on in terms of the overall water cycle in that whole area that drains into that lake, look at how the water level in the lake is changing. It's kind of integrating.
And this data, will it be publicly available? Like, who gets it?
Absolutely. That's one of the cool things about NASA is they're almost kind of radically open. So, as a matter of fact, the only people who get to see this data before it becomes completely free and open are a handful of people who are working on doing some of the first validation work, right? Where we're saying, okay, is it basically okay?
Water is, to me, and what makes me personally excited is the closest we get to life. People talk about, exploring Mars. What are they looking for? Water. So I think that is going to be something that having the best and most extensive information on our home planet is going to make a difference in people's everyday lives. So maybe not in my lifetime, but I'm convinced it will make a difference. So it's something that is not just an academic exercise. I think it's really going to impact and inform people's lives. And that's really what SWOT is all about.
A lot of the impact of SWOT will be felt by coastal communities. Rebecca went out to find out what that looks like.
My name is Barbara Blonder. First and foremost, I'm an associate professor of natural sciences at Flagler College. And the new job for me is city commissioner with the city of St. Augustine in Florida. We have a tidal gauge that is one of the National Water Level Observation Network gauges that's in Mayport, Jacksonville area. And that's the one to the north of us. And to the south of us, there's another one at Cape Canaveral. The distance between the two tidal gauges is 166 miles as the crow flies, which is a pretty significant gap if you're looking at developing local models for resilience planning. So we're working with what would be limited data sets to begin with that we're extrapolating from. And then those extrapolations are also affected by the fact that we sit pretty much smack in the middle of the two tidal gauges. And so it seems to us that SWOT would really help to fill that gap.
Can you tell me a little bit about what a resilience plan looks like and why these models would be important for it?
We have a number of different plans. We have stormwater plans. We have a resilience plan. We have coastal vulnerability assessments. All of these help us develop a picture of what our current state is and what we should be planning for. For example, our wastewater treatment plant is at sea level practically. It's just a few feet above sea level. And so how long will we be able to operate that plant? What can we do to protect it from storm surge and saltwater intrusion and accidental releases of wastewater?
I'm curious, you said that SWOT hadn't really crossed your radar, so to speak. What was your reaction when you saw what it would be doing?
Frankly, I was really excited about it.
Lauren, as fast as this technology is advancing, where do you see this heading? If you look forward a few years or even more than that, what do you think we're looking at?
I mean, I think we're looking at a future when maybe even an average citizen, if they want to find high fidelity imagery or data about a certain point on Earth, they'll be able to go and buy that data for their purposes because there are going to be so many companies that are selling this and making it more readily available as costs to launch come down and as more people understand the value of having this data. So I think it's only going to get better and sharper and easier to access.
Lauren Grush, thanks for coming on the show.
Thanks so much.
Thanks for listening to us here at The Big Take. It's a daily podcast from Bloomberg and iHeartRadio. For more shows from iHeartRadio, visit the iHeartRadio app, Apple Podcasts, or wherever you listen. And we'd love to hear from you. Email us questions or comments to bigtake@bloomberg.net. The supervising producer of The Big Take is Vicky Bergolina. Our senior producer and one of the producers of this episode is Catherine Fink. Our producer is Rebecca Chasson. Raphael Amsili is our engineer. Our original music was composed by Leo Sidran. I'm Wes Kosova. We'll be back tomorrow with another Big Take.